because I made a mistake earlier in the notes.
Obviously X, yeah.
Yeah. And it turns out it doesn't affect the final answer. That's why I didn't notice it. Because the integral of that whole thing ends up being 0 anyway. So now we can take the integral from 0 to 3, 0 to 2 pi of u minus u squared cosine v dv du. Okay, so I'll fix those sign mistakes a little later. Yeah. So, all right. So I trust you guys can work it out from there. So applying Stokes Theorem. So you're given a vector field, you compute its curl, you parameterize the surface that's enclosed by the curve. In this case, and in many other cases, it's convenient to use polar coordinates. Once you have a parameterization, you compute RU, RV, cross product to get the normal that goes here. And then you express everything in terms of u and v. Then you can go ahead and evaluate that integral. All right. So this happens a lot from the partial differentiation that results from computing the curl and these vectors, that you get a lot of expressions like this or this that tend to be pretty simple because certain partial derivatives turn out to be 0 or certain other things simplify. All right.
So you had suggested that we try the first way that you showed us, Stokes, I guess, version 1 first, and if it becomes too difficult, then to attempt using the curl method?
Well, a lot of it depends on, first of all, what is it that you're given, what does the problem call for you evaluating in the first place?
Okay.
So in this example, what you're asked to evaluate is this line integral.
Right.
So you can never do it using the old way, where you parameterize the curve and you take a dot product of f and the tangent vector. So you can just do it directly without using any theorem, or go ahead and go through all this to convert it
Okay.
and do that. On the other hand, if you're given a surface integral to evaluate, again, you try doing that directly, which would call for you computing the normal vector of a surface and all that. Or if you know that what you're integrating over the surface is a curl of some other vector field, either because you're told or because you can figure it out, then you can use Stokes Theorem going the other way and compute some line integral.
Okay.
Yeah, so that's why these examples have one in each direction. And that's really the choice you face on the exam. You're given certain integrals. In some cases, you're told, use this theorem to do it, but not always. So you either do it directly, just using how that line integral or surface integral is defined, or you use the appropriate theorem to convert it to something else, some other kind of integral, and try that.
And you had suggested it'd be really difficult one way and really easy the other?
Yes. However, by really difficult, it doesn't necessarily mean something like number 6.
Okay.
Yeah. What I mean is, if you do it the right way, it becomes quite easy.
Okay.
Yeah. Yeah. So I'm trying to swing the pendulum back the other way this time. So we're trying to compensate for the last exam. Okay. All right. So any questions about this one? All right. Now, one more thing that's comes out of Stokes Theorem is a physical interpretation of the curl. So suppose you have some point in space, we call it P naught, and you have it contained in a small disk, and the radius of that disk is so some small number a. So the disk, I'll call it SA, so it's a small surface, and so the circle that's enclosing it is the is just a curve we'll call CA. Now, what Stokes Theorem says is that a line integral over the circle of some vector field V is equal to the surface integral over the disk of curl V dot M ds. Now, let's assume that V is a velocity field. Of a fluid. Okay. All right. And then what we'll do is we'll let this radius A go to 0. Well, what happens in that case is as this disk is shrinking down to a point, then what we get on this side is roughly equal to a curl of V at this point. Because when you're integrating over a very small region, the integral ends up being roughly equal to the value of your integrand at a particular point. I mean, unit normal at that same point. Okay, so here's the normal n at p naught times the size of the region you're integrating over. So that would be pi a squared. So as a goes to 0, this surface integral roughly becomes this. You might recall, well, it would have been a while ago for any of you. Mean value theorem for integrals, which is closely related to the mean value theorem for derivatives that might be more familiar to you, that the integral from a to b of f of x dx is equal to the value of f at some point c in between times the size of a region you're integrating over, which is just e minus a. So it's the same principle that if, so as you're integrating a nice small region, you can just approximate the integral by the integrand at a point, p naught, times the size of a region, the area of that disk. Okay, so that's what you have on the right side. Now the left side I'm just going to keep as is for now. Give you a line that a is going to 0. Okay. Now, this quantity here, right, has a name. It's called the circulation of V. Around this curve. Now, if we keep in mind how we would evaluate something like this, well, this would be equal to integral from a to b, v of r of t, dot product with r prime of t, dt. So, looking at this, how would we make the circulation as large as possible? What maximizes the circulation? What is it about V that would make the that would maximize the circulation around this point?
Just want me to read it off the paper?
No.